Good morning. So, what did we learn yesterday? The basic least square algorithm. In a form y is equal to phi transpose theta plus v, and saw some properties and found that it is supposed to work well under certain if certain properties are satisfied by the data vector phi and the noise or error vector v. But first of all, now this is a basic algorithm. So what we will do today is first of all see some variants of the basic algorithm, very common variants, and so that in certain situations where these properties are not directly ensured, we have to do something so that in the modified formulation these properties are ensured. So if you once we do that, we will get the various variants. We will also do another thing, that is we will now today try to see, so far we have been doing just y is equal to phi transpose theta. Now we are interested in, generally we are interested in estimating transfer functions. So we will see that under various kinds of model properties and noise properties, how to form the equation so that it comes in the form y equal to phi transpose theta. Because we have seen that the algorithm can only be applied provided you can cast your model description in that form, right? So that's what we will see today. So first of all, we will see that we will consider a slightly different performance criterion. Previously we had considered this performance criterion, y is equal to y minus phi theta transpose. Previously this was not there. This we in our ordinary least square formulation we assumed that this is identity, right? Then it becomes a normal sum of squares and we got the solution for the least square case. Now we will put some w that is slightly more generalized. In what way is it generalized? That now we are not putting the same amount of stress on errors at the various instants. So it turns out that this is very useful in certain situations. In fact, this is very commonly applied in cases like adaptive control for some reason. So first of all, we will see that if we include a w here, that is if we are not interested in just a sum of squares but in a weighted sum of squares where we are doing weighting over time, that is k, then what is the solution? Okay, again you can do the same thing, just differentiate this v theta with respect to theta and set to 0, then you will get this relationship, which is obviously the same as our old relationship. If you set w equal to I, you will get the least square estimate back. And if w is diagonal, if w is assumed to be diagonal, then this v theta is nothing but what I said, that the errors at the various instants you are putting a weights. Actually I should put okay, So this EI is a confusing notation. We should put WI here, suppose, just to say that these are the diagonal matrix elements. So then you have weighted the errors at the various instants. That's what you have done. Now why should you wait? Why should you weight the errors at the various instants? Under what situation it may be necessary? One case is that when you expect that the parameters, see, you are looking for parameters based on data. Now the question is that if the parameters are constant, then all the data has been generated from one constant parameter and you are looking for it. So it makes sense to put the same weight on all the data points. But suppose now the parameter is slowly changing. It itself varies with time. So if it is varying with time, and if you are at the 1000th data point, suppose k is equal to 1000, then is it meaningful to give the same weight to the error which is being, to the error which happens at the 999th instant and the error which happened at the first instant? Actually, you should not put so much weight on the error in the first instant, because that error was actually caused by a different parameter. Within this 1000 instance, the parameter has also changed. So the parameter that you are looking for now, you should find out from the recent data, because the long past data has been, actually has been generated from a different parameter. So you should not put so much weight on that data. So in other words, you should give more weight to recent data and less weight to the past data. Then what will happen is that the estimate that you, as k is passing, so you are continuously getting new and new parameters. So then you will find that the parameter that you are getting will actually try to track the variation of in the parameter, because that will only give weightage to the most recent data, right? So based on this philosophy, you may like to find an optimal estimate according to this sort of a performance criterion. See what I am doing. This is yk. I is equal to 1 to k. Yeah. So what I am doing is that this is the parameter that I have got at the kth instant, suppose. So I have data up from 1 to k. Now using that, I am trying to predict what is yi. So I am trying to predict y1, y2, as well as yk minus 1, k minus 1, 2, all that. Now since the parameters are slowly changing, so it is not likely that you will be able to predict y1 using theta hat k, because y1 was generated using a long past parameter that has changed. So it is very likely that this error for long past data points are maybe large, but then you should not change your estimates because the long past errors are large, because the long past errors are likely to be large because the real parameter which has generated the data has changed. So you should discount the past. So this error should not get so much weightage when I is equal to 1. Rather, but when k is equal to, say, at k is equal to k, or at k is equal to k minus 1, or at k is equal to k minus 2, this recent past, there should not be large error. Then your parameter is wrong. So you should put larger weight on these recent errors. So that's what we are doing. We are weighting these errors by a factor called lambda to the power k minus I, where lambda is less than 1. So if lambda is less than 1, suppose lambda is 0.6, so first one is getting, so you are giving full, when I is equal to k it is 1, when I is equal to k minus 1 it is 0.6, then it is 0.36, then it is 0.216. So after some 7-8 samples, there is hardly any weight of the errors in the past, which is beyond the 7-8 samples. So which means that you are doing this optimization only based on the last, say, 7, 8, 10, 12 samples, whatever you choose. what value of lambda you will choose depends on at what rate you expect your parameters to vary. Usually actually this lambda is chosen very close to 1. I mean they are chosen something like 0.99, 0.98, because generally parameter variations are supposed to be slow. Why? What is the parameter after all? If the parameter is varying, why don't you call it a state? So actually, if you have two parameters, if you have two signals, one of them is varying very fast, another is varying very slow, then you can consider that for any reasonable time instant this is constant and this is the signal which is varying. So actually that's why you call it a parameter. Otherwise, if this one is also varying fast, you cannot call it a parameter. It should be called a state. So by the fact that you are calling it a parameter, even if it is varying, its variations must be much slower than the signals which you are calling states, right? So therefore, generally parameter variations are much slower compared to your sampling instance. They will probably vary by 10% over maybe 500 samples. So typically your data window should not be 5, 6, 7, 8 samples on which you base your estimate. It will be a few hundred samples. So that's why this lambda should be chosen, is usually chosen very close to 1. But it can be less than 1, and if it is made, even if it is made 0.99, it has a significant impact on the estimate. So now if we formulate this, then it's again simple. You can just again differentiate and get the solution for this case. And similarly, actually this means that in our old version, this Wi is equal to lambda to the power Wi is lambda to the power k minus I. Correct. So since this is an exponential, so this kind of a strategy is called exponential data weighting, sometimes called exponential forgetting, because you forget the past in an exponential rate. So if you just corresponding to this performance criterion, if you again rederive the least square algorithm and then again recursify it in the same old manner, you will get the same equation. These two equations are absolutely similar. This equation is different. So the covariance update equation is different at these 2 points. Other than that, these equations are the same as the least square equation. So they are very simple to implement. It's nearly the same. And it is used for identification of slowly time varying parameters, which is typically used in adaptive control. Because why are you trying to adapt your control? Because you expect your parameters to change. It may change depending on set points, because from operating point to operating point it may change, right? So this is used for such things. So this is our variant of least square number 1. We have, so whenever you expect your time varying parameters to change, you can use this. Next one is instrumental variables. This is a very quite powerful approach. It works really well, provided you are you can select your instrumental variables properly. We will come to that. What is the idea? That is where from this idea has come. The idea has come because sometimes it so happens that what do we want? We have seen that the least square algorithm gives an unbiased estimate only when this phi and v, there is elements of phi and the elements of the error are uncorrelated. If they are correlated, it will tend to bias, right? So now the question is that how can they be made uncorrelated? If it so happens that phi and v are correlated, what do you do? Because if you use least square, you will get a bias parameter. So the question is that can you not use some other parameter, some other vector in place of phi. Now what do you have to ensure there? What sort of a vector you should choose? Firstly, first property is that they must be uncorrelated. So you have to choose this new vector which you want to use in some way in such a manner that vector and v will be uncorrelated. Fact number 1. Fact number 2 is that in your least square estimate you have something like a phi transpose phi inverse. That inverse should not get disturbed, right? So phi transpose phi inverse should not suddenly become very large. When the phi transpose phi inverse is very large, then your parameter error will also get very large. So it should remain more or less like phi transpose phi. So in other words, the guideline is choose a vector, new vector, which is uncorrelated with v and very strongly correlated with phi. So if it is strongly correlated with phi means it is like phi. So if it is like phi transpose phi inverse, property will be maintained, while that vector is going to be uncorrelated with v. So you have to choose such a vector and then use it. How? So the whole idea is that you have this equation y is equal to phi theta plus v. This is your model. So what did we do? We actually multiplied it in obtaining least square. We actually multiplied this side by phi transpose. Then it becomes phi transpose phi. Then we multiplied by phi transpose phi inverse. That's how we got the least square. Correct? Rather than doing that, let us multiply by a new matrix called Z transpose Y. Then it will be Z transpose phi theta plus Z transpose V. So now, what is your theta? So now take theta as Z transpose phi inverse Z transpose Y. Suppose you calculate theta like this. So this one. Why do I want to do this? Because now this can be shown, this theta hat n. Now if in place of y you put this equation back again, then you will find that theta iv is the true parameter theta naught if your data was generated using the same model. So if your data was also generated by the system using the same model form but using some true unknown parameter theta naught, if that is correct, then the instrumental variable estimate can be shown easily to be just by substituting that y is equal to, so you will get Z transpose phi inverse Z transpose into phi theta plus v, phi theta naught plus v. This is how y has been generated, right? So now you got Z transpose phi inverse Z transpose phi, so you get theta naught, and then you get Z transpose phi inverse Z transpose v. That is your error term, parameter error. This is your theta tilde. This is the amount by which your estimated parameter is off from the real parameter which the system used. So obviously now, what do you want to do? You want to reduce this. So if you want to reduce this, you have to choose Z. Now you have to choose Z such that this remains invertible and not too close to singular, and this should be 0. That's what you want. So how to get that? So what Z you should use? That is the main question. So the algorithm is exactly same. Least square algorithm is exactly same. So the least square algorithm is exactly same. Only in some places, in place of phi, you have to use this vector. That's all. Now the question is, how do you choose this? That is the crux of the matter. So what's the idea? The idea is that now we will see there could be various ways of choosing this, and we will see how to choose this in the context of our dynamic system identification shortly. So I will stop here and we will again come back towards the end of this lecture as to how to choose xi when you are doing transfer function identification. You may choose xi in various ways for different kinds of things. It's not that always you are trying to do a transfer function identification, but then that is our main focus in this course. So we will come back to it towards the end of the lecture. Before that, let me first introduce that now all this phi transpose theta. So what phi and what theta we should use for transfer function identification, because we are interested in identifying dynamic linear time invariant discrete time dynamic models. Okay, if we are that we will discuss now. We will also have remarks of, suppose it is a continuous time model, how to do. So those are variants. So the basic idea is how to do a discrete time model. Continuous time model is nearly similar. So first of all, remember that, again coming back to model structures, that this is what you are doing. Actually you have a system, you have an input and you have an output, and this is your estimator. And in the estimator, what are you sending to your estimator? You are in the estimator you are sending measured input and measured output. Remember that they are not the same as this and this, because you have to use a transducer that may introduce measurement noise. You may find that you are giving the input from a computer, so you will say that I know the value. After all, I am giving the input, but the value which is there in the computer and the value which is actually going to the plant may be somewhat different because of several facts, because of AD converter characteristics, because of actuator dynamics. So many things may happen. So in general, first of all thing that I want to say is that the data that the system is generating, these input outputs, the physical input outputs which are there in the system, they are not the same as you are using in your estimator. Remember that. And you are going to build the model based on these two, not based on these two. Okay. So several other sources of factors are coming, apart from the fact that the plant itself may have disturbance which you have not modeled. So in general, all these effects, this disturbance, this noise, any dynamics which you have ignored, so all such things you are going to. So basically what you do is, in your model you try to say y is equal to some function of u, which is your controlled known input, this one that you use, plus whatever is the rest, you say that is some noise term, and you want to characterize that noise term. So that means that you have to choose such a model, so when you are trying to estimate, you have to choose what kind of thing is this, what structure is this, and you have to choose what is the property of this, all these that you have not modeled, and all these that you have chosen to describe by the term noise. Now, what is its characteristic? Does it have a DC component or not? Because you must at least get some idea of these components, because otherwise those nice properties that you are assuming, that this part will be zero mean white and all, those things will not come, and they will give you bad estimates on these. So you must, when you are selecting a model structure, you must put thought on what you should put here, and how you are going to characterize this. So these are the two things that have to be thought about. Then you have to decide on the model structure. Then after you have decided the model structure, you have to do parameter estimation in that structure. So typically a model has two inputs, u and v. This one you explicitly use in your estimation equation. This one you don't know, so you have to do something based on the characteristics of this that you can find out, maybe by doing offline experiments, something. So effects of u and y should be modeled as per system dynamics. Obviously, if you think that this is like a third order system, from physical considerations, from RLC circuit, from motor model, whatever, then this part obviously you would like to characterize by a third order system, because so you will choose a third order model for estimation, and this part you should choose depending on what all knowledge you have about disturbances, about noise sequences, right? So that's how you have to choose. So what are the typical model structure which are used? For For example, the simplest model structure that is used for estimation is this one. Now we are talking about dynamic system estimation. No, we are not saying phi transpose theta. We'll see what is phi and what is theta exactly in this model. So in this model, people assume that y and u, that is a measured y and the measured u, are related by this relation. It's an assumption. So I mean, you can have certain observations about this. For example, you can say that you can see that if you do this, you will find that y is equal to b by a u plus 1 by a v. From this, just simply divide by a. So this is your input transfer function, and this is your noise transfer function. So you are assuming as if the data is generated by u, here b by a, and here v also coming from 1 by a. So this a you are assuming to be common. Why? That means you have, if you use this model structure, you must have some basis of thinking that the model structure, that the any noise that may be coming is also coming through the same set of poles, which means that it must be some noise structure. Now what is that signal which gets filtered through the a polynomial? It is the state, because what is the state to input? What is the state to input transfer function? That has Si minus A inverse. So that means that that means that the A polynomial, which is the determinant of Si minus, or in this case Zi minus A, is coming in the denominator. So by which you mean that this noise must have, just like u to x has that pole 1 by A. Now V is also having this 1 by A. That means V must have entered along with u. So you are kind of assuming that noise is also being processed by the system. So people sometimes, there are people, you may not always be able to justify such things, but actually what you should do is in a practical situation, what people do is that people do trial and error. Sometimes they will try some things. That is, they will first make some selections based on their understanding, what kind of noises they have, what kind of calibration experiments they have done, etc. And then they will also try some numerical experiments. That is, if they are not satisfied with the kind of parameters that are being obtained, then they will change the model and then again try. So it is not that you will be able to arrive at the structures always. And these structures are popular because it is also a fact that sometimes very simplistic structures are dealt with in textbooks because they give rise to very nice analysis. So fine, but they also will reasonably work. So let us first look at this model structure, which is the simplest. It is called ARX, or auto-regressive with exogenous input. A for auto, R for regressive, and X for exogenous input. Exogenous input is U. So you have, when you have, these are terms which are used by the stochastic process community. So in such a case, you can easily understand that how can I cast this model into this phi transpose theta form, because we need to cast it, and our algorithm uses it in this form. So you see that this model you can nicely cast in that form. For example, phi can be this. What is this? If you write it in time domain, it will become what? It will become A is, see, one of the parameters of A and B you can normalize. So I have chosen to normalize A0 as 1. By A by B, any one parameter can be normalized. So I have chosen to normalize A0. That is the usual custom. So in that case, what do you have? You have, if you write this equation in time domain, you will have yt plus a1 yt minus 1 q inverse plus an yt minus n is equal to b0 ut. This term you may or may not have. This is a direct term. If you have a D matrix, then you will get this ut minus 1 and so on, plus vt. So if you bring these terms to the RHS and then arrange it in terms of this form, you will get. So you will get minus a1 yk minus 1 minus an yk minus n. This minus, either you make this minus or you make this minus, doesn't matter, and then b0 uk and bm uk minus m. So this is your phi transpose k plus v. So you see that so this system you are now able to cast in this form, and then you can apply least square. If this v, now the question is, you can always write it like that. You got some y's and u's, you can always look for a model in that form. When will it work? Only when you think that this v is going to be zero mean white. So if this v is not zero mean white, then this is not going to work. Firstly. Secondly, only v being zero mean white will not do the job. V should be uncorrelated with u, because v should be uncorrelated with phi, and phi contains this. So v should be uncorrelated with u. When does that happen? When the system is not operating in closed loop. If the system is operating in closed loop, then you are computing u based on y, and y contains v. So your u contains v. If you are using a feedback control law, then you are calculating u based on y contains v, so therefore u contains v. So therefore this and v are going to be correlated. So if you make these assumptions that they are uncorrelated, then phi will be uncorrelated with v, and then you can expect good results by applying ordinary least square, but not otherwise. So what do you do if that does not happen? Then you have to use, that means that you have this description assumption. If it is wrong, then you have to see how you can improve this description. If this really does not turn out to be zero mean white, then what is it? Find what it is and try to model it. So you can get this. So sometimes people will say that no, I will assume that now this term previously which was being assumed white, now they will assume that no, this may not be white, but it may be a term like this where this is white. So what does it mean? Now you are assuming that this term which you previously assumed white is now a sum of some white terms, which means that its autocorrelation function is not like delta, but it will spread little bit. Depends on what is the order of the C polynomial, because you are taking weighted average of R white signals. So now your autocorrelation function is going to spread. So it is not like a delta, not ideally white, but it will not be. It may be correlated with the past sample, but it will obviously not be correlated with 30 order samples maybe. So now you have assumed such a thing. So you have relaxed your noise model assumption because you found that the previous model does not work. So now again, you see, now what do you have to do now? This is my model description, and this is how data is generated. You are assuming. Now you have to cast this kind of description into a phi transpose theta form such that the residual is white. Unless the residual is white, you are not going to get true parameters. That is sure. So now how do you cast this into phi transpose theta form? Such that whatever will be remaining with phi transpose theta, that part will be white. That may not be exactly this. So what you do is, you try to do some manipulations. That is, you first divide this thing. You have to this is the model. So you have to, the whole idea of doing this is that you have to write the model as y is equal to something plus white. You have to express this model like this. So first of all, how do you express this something plus white? This is white, but this is CQ inverse is there. So first I will divide. So I will get A by C. See, this was my equation. First I will try to make this term white. Let me try to make this part. Then see what comes here. So I will get A by C y is equal to B by C. Sorry, this is U minus V. So I have first of all got it into a form where this is white. Now I want to write it as y is equal to something plus white. So I will now write y is equal to this side. I will write 1 minus A by C y. I can write that. Can I write that? No. It should be minus, no? Plus B by C U minus V. Now what is the beauty of this 1 by, I mean, is it just 1 minus? Actually, if you compare, see, incidentally in this C matrix I have chosen this as 1. Why it cannot be some arbitrary number C naught? After all, what am I trying to do? I am trying to, with this C matrix, what I am trying to do? I am trying to model the power spectrum of V. Remember that V is a stochastic variable. It does not have value. But you don't know what is value. So all you can do is that you can model its power spectrum. Now if you are modeling its power spectrum, you can always put this as 1 and then adjust the variance of V. Nobody is saying that V is going to be a white signal. I mean, a white signal of what variance? I am not saying that it is a white signal of unit variance. So if this is C naught, make its variance C naught square and then make this polynomial 1. So the idea is that you can always choose it as 1 and then adjust the variance of V such that the noise power is modeled. So that's why people can choose this as 1. So if you choose it as 1, remember that this thing, that is 1 minus A by C, only contains past terms of Y. So it will contain, because here is 1, C naught is 1 and A naught is 1. So when you do 1 minus A by C in the numerator, you don't have any direct term. So you have only past terms. So which means that this is now going to be a vector of past terms. So this will only contain y t minus 1, t minus 2. You can just experiment with any example. Just put values and try. So this is going to be a function of past values of y. This is going to be a function of u, and this is going to be a function of v, and this is going to be y. So now I have to write this equation in term. If I can write this as phi transpose theta, this part, then I am done, because then whatever is remaining is white, and then I can apply LSE, right? So that is the idea. So now what they have done is, but the main problem is that how do you write this one, because this is not a linear term. This is not. Can you write it as phi transpose theta? There is a CQ inverse at the bottom. So you have to do some clever manipulation such that it can be written as phi transpose theta. So what is that manipulation? That manipulation is that if any, you know, by now at least this much you should know, that if something is some quantity plus white, then what is its conditional estimate? Only that part, because this is a function of y t minus 1, t minus 2. So therefore this is given, and this is all known. So this is given, this is white. So what will be, if A, B, C are given, then what is the conditional estimate? Only up to this part. White part I cannot estimate anyway. So this is your conditional estimate, this A marked part, these two terms. So then what is your prediction error? Given the past data and theta, it is this much. So now what you can write, so now you see that you can write this equation, the same equation, in terms like this, where this is a prediction error, and this is a V. Once you can write it in this form, then you know that you can put it in phi transpose theta. What is the catch? The catch is, how do you know this? Who gives you theta? Theta is what you want to estimate. So nobody will give you theta, ABC parameter values. Who will give you? How will you compute this? If you want to put it as phi transpose theta, this will become elements of phi. But for computing this, you need theta, and you don't have theta. So the whole idea is that if you don't have theta, then you use what you have. At least whatever estimate of theta you have, you are going on improving your estimate. So at any point you don't have you may not have the true estimate, but you have some estimate. Use that. That will also improve the picture. So what you do is, so people, whatever is the latest estimate of theta available, people will use that to compute epsilon t theta. So then you can put it in phi transpose theta form. Remember, now a very interesting thing comes. That is, phi itself is now a function of theta, because the elements of phi are now functions of theta. So the basic premise of linear regression is now violated. It is this equation y equal to phi transpose theta does not remain linear in theta. Previously it used to remain linear in parameters. Why? Because whatever is the elements of phi, at least it does not contain theta. Now that is violated, because we are now computing elements of phi using theta. That is why it is called pseudo linear regression. It looks like linear, but actually it is not linear. But anyway, whatever it is, at least you have done something. You have tried to model this thing, and you have put whatever best you know about theta to be able to compute it in a phi transpose theta form. Now hopefully, as theta estimates will improve, this computation will also improve, and that will give further boost to your theta estimation. So it is like recursive, as the estimation of theta improves, this estimation improves, therefore the estimation of theta improves. So hopefully they will aid each other rather than destruct each other, and that is a rather difficult thing to prove, that it will actually aid each other and result in a better estimates of A and B. You are actually mainly interested in the estimate of A and B. You are modeling C because you want to improve your estimate of A and B. That's why you are doing it. You are generally noise models are not directly used, especially in control. So this model is called Rmax. Previous one was ARX. Why? Because it contains an autoregressive component, it contains a moving average component. Now it's an average of white noises, and it contains exogenous input. So AR, MA, and X. Previously it was only V, therefore it was only AR and X. Now it is AR, MA, X. Okay.
In ARS model also we had V.
In ARS model we had V, but we did not have a moving average of V. There we assumed that the input is only a white noise process. Now we are considering an average of white noise processes. So I am generalizing my autocorrelation assumption. Previously I put a stringent requirement that this V should have a delta-like autocorrelation function. It should be uncorrelated with even the earlier sample. Now I am saying that no, it can be little correlated with the past 2-3 samples. That is very likely. It is very difficult to get a totally uncorrelated signal. This page I will not go into. You can do further generalizations. You can assume a model like this, which is the most general model used. Totally different CD, totally different BAF you can use, and then you can go along the same approach and still cast it in phi transpose theta form. That you will have various other vectors, and these are generally not called for, and it's not that simple that you will you might experience convergence problems, especially when you have large amount of noise. So you can do it, but it's not, you have to do it with caution. Just by generalizing the noise model you won't always get more improved estimates. So we'll skip this. This is just to show that it is possible to even further generalize it, and it is done in the literature. Now we come to the instrumental variables model. So now remember that we wanted to choose a vector xi which will have that property. It is well correlated with phi and not correlated with v. That's the property that we said if we have, then our parameter error will be low. And what is the advantage? That I don't have to extend my phi. Remember that my phi size is the same. Only in place of phi, in some place phi is y and u. See, in the earlier approach also I am trying to take care of this correlation between phi and u, phi and v. But there I am modeling v and then extending phi and then making my approach more complex. All my vectors are going to be of higher dimension. Computation load is going to be larger. Here that is not going to happen. Here it just contains y and u. So I mean nice and small. But I have to choose. But nothing comes free. So I have to compute this instead. These elements. So what people generally do is that just in place of y and u, they generally use different values, because this is anyway uncorrelated with phi. If you are having uncorrelated with v, if you are having open loop experiments, if you are having closed loop experiments, you have to do totally different approach that we will discuss later. We are always assuming that our u and y have come from open loop experiments, not closed loop experiments. Okay. So you have to choose this such that it is well correlated with this but uncorrelated with v. That is the approach. It's 11:30. 2 minutes. So one approach is, why don't you put x is the same as u but little delayed. Why do you have to delay it? Because if you just repeat this, then this matrix will become rank deficient. You cannot just repeat this. Columns will become same. So just to preserve that rank thing, you just delay it. But if the system, how much will you delay it? What is this d? You want this to be well correlated with y. So you have to know that suppose your system time constant is 20 seconds. So you know that at least y now does have some effect of u k minus 10, because the time constant is 20 seconds. So at least over the last 5-10 seconds, the u and the y are going to be correlated. So if you choose a u here, and if you choose d of typically less than the time constant of the system. Now the point is that how do you know time constant? You are trying to estimate the model and you are making assumptions about time constants. This itself is a contradiction, but it usually happens that after all you have some idea about the system. Estimation of time constants you can do, order of time constants, not exact value, you can do very easily. For that you don't need any, just a simple step response experiment will tell you what is the time constant. What is the order of the time constant, whether it's 10 seconds or whether it's 100 seconds or whether it's 1 second. That's very easy to determine. So if you have an idea of that, then you can, one very simple choice is just use delayed inputs. So now this vector only contains inputs, so it is uncorrelated with v. That requirement is satisfied. And since uk minus d is naturally going to be correlated with these, because you have done the shift within time constant. If you have done the shift, if you make this d too large, then it may become uncorrelated, right? The other one is that why don't you first you do a simple recursive least square. You know that you will get some parameter bias, fine. So you got a bias parameter b bar and a bar. Now use this b bar and a bar to simulate x using the same u. So obviously it will not match with y. Remember that now it becomes a pure function of u. B bar and a bar are constants once you have chosen them. So now this x is a pure function of u. It does not use y. So once you use, it becomes a pure function of u, it is again uncorrelated with v. Fact number 1 established. And the second is that even though these parameters are slightly erroneous, this x is going to be highly correlated with y, obviously. There may be some error, little bit error. After all, the least square algorithm works. So another approach is just you use some approximate least square and then go on simulating x along with y using the same u, and then use this x here. Can give you a significantly better parameter estimate when you have correlated noise. This algorithm really works well. Okay, so we'll stop here to say that we only did that the good properties of LSE are obtained under restrictive conditions. So we saw that under some other condition how are we going to work. So we saw basically two approaches. One is called instrumental variable, another is called recursive prediction error approach. Now this prediction error, that is everywhere we are trying to use epsilon t given theta, which is y minus y hat t given theta. This we are using for various model structures. So such methods, this class of methods are called recursive prediction error methods. So we saw some examples of this and this. And for time varying parameter systems, we saw that you have to have a weighted least square with maybe some exponential forgetting. But if I stop here, then it will appear to you as if least square algorithm is the only estimator in the world. That is, it is not the case. There are estimators which you can derive under from other philosophies. So I think it is important to I mean otherwise you always tend to feel that the least square is the only estimation approach. That is not a fact. So we will try to look at least some other estimation philosophies like maximum likelihood, like maximum a posteriori methods, like Bayesian estimation methods. So that is all for today. Thank you.